part 1. So in this session, we are going to see the part 2 of unit 4, which is optical fiber measurements. So the different measurements which we are going to do in optical fiber is what we are going to deal with. So what are those measurements? We are going to see the important parameter of a fiber when it travels from one point to another point. When it travels from one point to another point, the basic measurement that we have to do is attenuation. So attenuation measures the amount of loss of your information or loss of your signal along the fiber. So that is fiber attenuation. So that measurement should be done. Next is that refractive index. So the determination of the refractive index is a major factor when we go for TIR, which is total internal reflection. So the core refractive index and the cladding refractive index is an important parameter that should be measured such that appropriate design for optical cable can be done. So the refractive index profile measurement or the RI profile measurement. Next is the fiber dispersion measurement. So the amount of signals that is being distorted either in the form of intermodal distortion or intramodal distortion is to be determined. So that is what interdispersion measurements, or simply we call it as dispersion measurements. So obviously we'll be using multimode transmission in some places, we'll be using single mode transmission in some places. So whenever we use a single mode of transmission of the optical fiber, we do not get distortion mostly. So whenever we migrate to a multimode structures, so then there the concept of overlapping of optical signal one with the other signals takes place. So this leads to dispersion. So that measurement is to be done. Next is the basic measurement, which is the numerical aperture. So numerical aperture can be found out by the refractive index. So the refractive indexes are known, easily you can find numerical aperture. So there is a procedure also for finding numerical aperture. So we'll see that. The last measurement that is necessary for an optical fiber is the diameter. The diameter of the core, diameter of the cladding is to be measured, such that during coupling process, appropriate measurements has to be done. If you couple two different fibers, which is having fiber one having the core diameter of some 10 micrometer and cladding of 15 micrometer, then fiber 2 you are having 15 micrometer of core and 25 micrometer of cladding. So when you couple this, the cladding of the first fiber will be equal to the core of the second fiber. So this has to be avoided, such to avoid losses. That's what fiber diameter measurement is important. So how do we measure the attenuation? So attenuation is a loss of optical power as a result of absorption, scattering, bending, core cladding losses, or many things as the light travels through that optical fiber. The total attenuation is a function of the wavelength of light lambda. So the total attenuation between points x and y in the fiber can be given as attenuation A is equal to 10 log to the base 10 px by py between those 2 points. So where px is the power output at point x, py is the power output at point y. Point x is assumed to be closer to the optical source than point y. The most widely used method for measuring the total fiber attenuation per unit length is the cutback method or the differential method. The experimental setup for the measurement of the spectral loss to obtain the overall attenuation spectrum is shown in the following figure as here. So this is a cutback method. we have a light source or an optical source which is being illuminated by an LED or an laser, so that falls on a lens. So this is your lens. On this lens, using a chopper, the signal is chopped such that the light converges at a point in your monochromatic place. So this is your monochromatic film. So from this, a lens will be present. So that lens will again divide it in the order sorting filter. Then with reference to a reference signal, using viewing optics, we can view that. The same is being transferred to an objective. Then it is given to a mode scrambler and to a cladding mode stripper. Then we will be having the optical fiber, which is this. So this fiber, when it goes on. Then we have the cladding mode stripper, the same. Then we have the index matched photo detector. Then we have a lock-in amplifier. Then the recorder or display, such that the attenuation is being measured. So measurement procedure is that setting up a white source using a xenon arc or a tungsten halogen, which is the older method. As I said, LED or laser is being used nowadays. The older method uses xenon arc or a tungsten halogen. So this enables the lock-in amplifier and the receiver to perform phase-sensitive detection. Then the chopped signal is then fed through an monochromator that utilizes a prism or a diffraction grating arrangement to select the required wavelength at which the attenuation is to be measured. Then the light is filtered before being focused onto the fiber by means of a microscope objective lens. A beam splitter is used to provide light for viewing optics and a reference signal. A mode stripper is included at the fiber output end to remove any optical power that is scattered from the core into the cladding down the fiber length. Then the cutback method involves taking a set of optical power measurements over the required spectrum using a long length of the fiber. Then by using the following relationship, optical attenuation per unit length alpha dB for the fiber can be calculated. Unit is equal to alpha dB is equal to 10 divided by L1 minus L2 into log to the base 10 of PO naught divided by PO1. So PO naught and PO1 are the optical power outputs. So in terms of electrical voltage, they can be written as alpha dB is equal to 10 divided by L1 minus L2 log to the base 10 of V2 by V1. So there are some drawbacks of this method. Drawbacks is that the drawback of cutback method is a destructive technique. So several other non-destructive methods are being used, like the substitution technique, backscatter measurements. So any queries about this cutback method, you can type in chat box. So let us see an presentation on the cutback method that is used for measuring optical fiber loss. Hello, sir. வந்திருக்காரு சார். அவர் வரண்டாரா சார்? அவர் வரண்டாரா சார்? ஏதோ பார்க்குறேன் சார் போயிட்டு. நான் இன்னும் ஓகே ஓகே சார். ஏதோ போய் பார்க்குறேன் சார். சரி ஓகே சார். ம் சரி.
Good grammar and spelling are important, but if you want to write essays that inspire, messages that forge brighter connections, and emails that get the job done, you need to think about more than just grammar and spelling. This sentence is grammatically correct, but it's wordy and hard to read. It undermines the writer's message, and the word choice is bland. Grammarly's cutting-edge technology helps you craft compelling, understandable writing that makes an impact on your reader. Much better. Grammarly works where you work, on your computer or your phone. Imagine what you could do with the secrets of the world's best writers at your fingertips, anytime you need them. Are you ready to give it a try? Installation is simple and free. Visit Grammarly.com today.
This is the 16th lecture in the fiber optic Association series on fiber optics. Lecture 16 is about insertion loss testing. Insertion loss testing is a test method that simulates the accuracies on fiber optics. Lecture 16 is about insertion loss testing. Insertion loss testing is a test method that simulates the actual system operation. It uses a light source and power meter, sometimes called an optical loss test set, and patch cords, which are used for launch and receive reference cables. Insertion loss testing works like a fiber optic data link. The data link has an LED or laser transmitter that couples light into the connector at the end of the cable plant. As the light travels down the cable plant through the fiber attenuates the signal, and connectors or splices will cause loss in the signal. Eventually, the signal exits the connector on the far end of the link and is detected by a detector. Insertion loss testing essentially mimics exactly what's going on here. So if we set it up correctly, it will give us a loss value for the data link that is appropriate to the system we're using. The critical question is, what should the loss of the cable plant be? And the answer to that is something we calculate during the design phase of the network. We look at the cable plant, the fiber, the connectors, the splices, and the couplers, and from that we calculate a link power budget, which tells us how much loss the cable plant should be. The second part of the link power budget is to look at the transmitter power and receiver power requirements of the system that we're going to use on the cable plant to ensure that it will operate with the projected loss of the cable plant from the link power budget. One of the instruments we need to test insertion loss is a test source. The source should match the transmitter type and wavelength that we're going to use in the communication system on the cable plant. Typically for multi-mode fiber, it's an 850 or 1300 nanometer LED, and for single mode, it's a 1310 or 1550 laser. We use the source connected to a launch cable to connect to the cable plant under test. It's important to test at the correct wavelength because the loss of the optical fiber is very much a function of the wavelength of light. Basically, it's caused by scattering, which is highly dependent on the wavelength. So we want to test the fiber at the wavelength that we're going to be using the cable plant at. For example, in multi-mode fiber, the difference between the loss at 850 and 1300 nanometers is approximately 3 dB per kilometer at 850 and only 1 dB per kilometer at 1300. The difference can be startling. The other issue with multi-mode fiber is the source type. The fiber loss is a function of what we call mode power distribution. We recommend that you look at the FOA online reference guide to get a more detailed view of all this. But basically, it's the fact that the core, the center of the core of the optical fiber, has higher loss in the outer sections. So LEDs fill the core more thoroughly and have higher loss than an LED, which only transmits down the center. What we do is we condition the source to be generally acceptable in the industry. The way we mostly do that is by using a source of known output and a mode conditioner that is typically done with a mandrel wrap, as is shown here with this source. And that will condition the signal to send light down about 2/3 of the core, but in a very consistent fashion so that we can compare our measurements with what others would measure on the same cable plant. The power meter we use is the same as we use for any other measurement of optical power. It's a specialized light meter. It adapts to fiber optic connectors and is calibrated at the proper wavelengths. The measurement ranges of the meter are both in dBm for measuring absolute power and dB, which we use for measuring loss. Most power meters will have a dB range that allows you to set a zero reference value and read loss directly. Another instrument used for measuring insertion loss is an optical loss test set, and that's basically nothing but a light source and power meter in one package. The other important equipment or component we need for insertion loss testing is reference cables. Reference cables are used to attach the source to one end of the cable plant and the meter to the other. They launch the light from the test source into the cable under test, and they mate with the connectors on the cable so that we can test the loss of the connectors on either end of the cable plant. It's the launch cable we use to control the modal distribution in multi-mode fiber. Reference cables must match the fiber type in the cable plant we're using, and of course the connectors must be able to connect to the connectors on the end of the cable plant. But the most important thing for insertion loss testing is to make sure that the reference cables are high quality. That means the connectors have low loss and you keep them clean. The way to do it is check them with a microscope, and if you see something like this picture, you clean them regularly. You always clean your connectors at least every few insertions, and you inspect it with a microscope, because the continual mating and unmating with the cables you're testing can cause the connectors to become scratched or worn, and therefore they're no more good for testing loss. You'll get high loss with every measurement then. There's a convention that you have to understand in making insertion loss measurements. Loss is generally referred to as a positive number, so we say the loss is 2 dB. And an optical loss test set, the combined meter and source, will generally read that loss as 2 dB. But if you're working with a meter that has a 0 dB reference set function and a separate source, and you set 0 dB reference at some value, when you measure 2 dB, it will read as a negative number, minus 2 dB. But it's always the same loss. In effect, there are people like us in the industry that feel that the optical loss test set should also read minus 2 dB since it's a loss, but
Yeah, if you have any queries or doubts, type in chat box.